Yes, class. Is it audible to all of you? Austin, Tarif, Faiza, Madiha, Shahid,
Yes,
Rabia,
ma'am.
Chavez. All right. So in the last class, we had completed till dipole and the relation between electric field and how does it vary with dipole. Right. So this was the formula which we had obtained. V is equal to Kp cos theta by r squared. This is the generalized formula. If we are specifically asking about axial line, for axial line, we'll put theta as 0 degree. So our formula will come out to be directly, if you will put in this formula, this will come out to be Kp by r square. And in equatorial line, when you will put theta as 90 degree, directly cos 90 degree, your equatorial line, this will come out to be 0. So that was all about potential. One very important relation we had seen, which consisted of two important portions. First one said that electric field's magnitude, this is directly proportional to the potential gradient. So when do we call potential gradient? We call potential gradient when anything is termed as gradient when anything gets changed with respect to distance, with respect to position. So here what is happening? Here potential is getting changed with respect to distance. So that is what is meant by potential gradient. So electric field's magnitude is directly proportional to potential gradient. But we have a negative sign in our formula when we write E is equal to minus dV over dr, or even when we are writing E is equal to minus V by R. That time we put a negative sign. So what is the significance of that negative sign? Basically, that negative sign says that electric field decreases in the direction where potential increases. Fine, that's why we have a negative sign. So these were the two important results which we had seen. Now, some questions.
Ma'am,
Yes.
can you once again just explain why, how is it proportional to potential gradient electric field?
See, how is it potential to potential gradient? This you can see by the derivation. See, work done is equal to force into displacement. Your force is charge multiplied by electric field, QE. This is how we write the force, no? QE.
Yes.
Multiplied by the distance dr. Fine, this is one work done, one equation of work done. Secondly, you have work done's equation through the definition of potential also, that this is charge multiplied by change in potential. So two equations you have obtained, QEdr is equal to QdV. QQ gets cancelled. From here, you get the magnitude E is equal to dV over the dr. So this is the derivation. This derivation is asked also in your exam. In your long questions also this is given. But if it is given in your long questions, then this part will be given along with a mention to the significance of this negative sign or two important conclusions that you can derive from this. So if it is asking two important conclusions that you can derive from this whole derivation, you have to mention that electric field is directly proportional to potential gradient according to this derivation, and you have to mention about the negative sign as well, that electric field decreases where the direction of potential increases. So this is the derivation also in your 3-mark questions. Only this derivation part, establish a relationship between electric field and potential. This can also be used. And apart from this, no class, not just for this specific question or not just particular to your potential part, in other lessons also of your electromagnetism, when you will be moving, because your first book is completely based on electromagnetism. You have starting lessons of electrostatics, and the last lessons are also electromagnetic waves. So throughout anywhere in your calculations, this relation can be used. That's why this relation is not just important for your examination point, but for your calculations perspective also, this is important. We didn't practice any question from this. So let us practice some questions from this part. Then one topic, remember in the last class, I have told you up from this only that partial derivation is also there. We sometimes partially derivate this. So that I'll also take. But first, let us quickly revise the question. Some questions let us see. Okay. So this question says that if V is equal to KQ by X, what is electric? Fine. It is saying, see, electric field's relation is what? If here you are given X, so we won't write dr. This means we'll write dx. So E is equal to minus dV over dx. This is how we write the formula. This is what is the formula. Now, electric field. This is given as potential's value is given. Right, the value of potential here is given. It means you are differentiating minus dx. What is the value of v? The value of v is given as kq by x, right? So from here, I can say this is given as electric field is given as minus kq because this is constant dx. This becomes dx divided by x, right? If we are differentiating, this becomes dx divided by x. Or the best ways to solve this part is just by bringing x up. That's how your questions of derivations will get solved. Anything is present in the denominator. Fine. Anything is present in the denominator. You want to differentiate it. You want to solve it. The best method is to directly bring it up to the numerator. Fine. So here this is given as if v is equal to kq by x, what is the electric field? So E's value we have written as minus dv over dx, right? And E is equal to minus kq x to the power minus 1 dx. So see, if we differentiate this part, this is in differentiation only, no? Minus kq remains constant. We are differentiating this part, dx. I won't write this in the numerator because if we are differentiating this, then this should come here, right? Same thing, this d should come here. Then only this will be, this seems as differentiation. So now see, minus kq, this is constant. Differentiating x, we are differentiating x. So see, minus 1 comes, how to differentiate? X to the power n. This is written as nx to the power n minus 1. This is the generalized formula for differentiation. So here your x to the power n is what? X to the power minus 1. Your n here is minus 1. So it's like x to the power minus 1. Your n is minus 1. So first step is 1 in minus 1 into, right? Nx. So minus 1x, n minus 1, minus 1, minus 1. Just substitute n is equal to minus 1 in this formula. That's how you will get. So minus 1, x to the power minus 1, minus 1. That's it. So this becomes minus kq into c. This is getting multiplied by 1. So that becomes plus kq and x to the power minus 2. So what we can do, we can shift this x to the power minus 2 here. So that becomes kq divided by x squared, right? And that is the general formula also of electric field. Yes, right? For point charges, what is the formula of electric field? Kq by r squared, that is what we write. So you can relate it from here also. Potential's value is kq by x. Here x is given, just write in terms of r, you will understand. Kq by r is the formula for potential and kq by r square is the formula for electric field. This is it. So you can see from here also, if you are using the same relation, you are getting back the electric field's exact value, which you have already studied. All right, note this down. This is just derivation of v is equal to kq by x. Just derive it, you will get the electric field's value. Note it down.
Ma'am, do you have to write this?
Yes, yes, these types of questions will come in MCQ. Just note down this page as well.
Yeah.
Someone is asking. Yes, Chavez, you were saying something?
So I was asking whether you have to write this or not.
Yes, yes, you have to write this. And Faiza was also asking the same thing. These types of questions, no, which you have written, this can come in MCQ also, Faiza. This can come in MCQ because actually this doesn't take time. If you know how to solve this question, This won't take your time how to solve it. It was just a very 1 or 2 liner question. Actually, this is a very short question. So not in your derivation it would come. This isn't part of derivation. In your derivation, the only above part was there. But in your MCQs also it can come in your very short mark questions, 2 markers, it can come. It can come. No, Tari, we didn't integrate here. We differentiated. See, here differentiation is occurring and we put the value of potential. So we differentiated this term, not integrated. Here you are asking, here Faiza.
Yes, ma'am.
No, see, when we differentiate, no, either initially it's this, and afterwards, when you have differentiated, this is just dx is there just to show you that you are differentiating, right? Now, when you have used this formula, this is the formula of differentiation. So that's why dx is not there. That was just a function to differentiate. It's like if you are differentiating x dx, x over dx, so or dx over dt, any variable, anything. When you are writing nxn as this, right? Then this t doesn't have any significance over here because you have converted into its main form. If you have written, try this question, v is equal to 3x cube, find electric field at x is equal to 2 meters. This is not difficult. V, again, potential's value is given, find out electric field's value. How will you find out? Using this relation. And then put in the value of x.
Ma'am, electric field is equal to negative of potential gradient. Right?
Yes, yes, this only you will use. Differentiate potential with respect to x. Yes, Madiha, right answer. So Madiha has already given the answer for question 2. Look class, this is given to you as V is equal to 3x cube. Now you are differentiating minus dV over dx, right? So basically you're differentiating what? 3x cube d over dx. So again class, that's why I had initially discussed differentiation and integration with you before starting with this lesson. So all those who are having confusion, please understand. Remember we did when function gets multiplied with the variable. No, Chavez, some error I think you are committing while solving. Just check your calculations again. 3 is a constant term. We keep the constant as it is. Now how to differentiate x cube? This gets multiplied here and minus 1. That's how we write, no? N is there, nx to the power n minus 1. Nx when x to the power n is there. So here also x to the power 3 is there. That becomes 3x to the power 3 minus 1. Right? And a constant term, already this constant 3 is there. This is the constant 3. So we have this term. So what does it become? A 1 minus sign is also. Yes, Chavez, now your answer is right. Chavez, one thing, whenever you're answering, try to put in the units also. You are answering electric field. So what should it be unit? Now your answer is good. So Madiha and Chavez have answered it.
Sure.
Minus 9x to the power 2. This is electric field. Right. Now value of x is given to us. Value of x is already given to us as 2 meters. So at x is equal to 2 meters, electric field will become minus 9 into your 2 square. So that becomes minus 9 into 4, which is minus 36. Electric field is Newton per coulomb. You can write volt per meter, any unit of electric field you can use. It's just that volt per meter also is not different for you now, right? Initially, volt per meter was different. But now you have seen potential, after seeing the relationship between potential gradient, this is minus 36 Newton per coulomb. SI unit can be volt per meter as well. So any unit you can use. All right, note down this one. Yes, Madhya. Third question's answer is also right. Yes, Tari, please. In your assignment also, these types of questions will be given. Meanwhile, try this. Potential difference between A and B is 20 volt. Calculate electric field. This is a very easy question, very easy. This will just take few seconds to calculate because values are also given easy. Madhi has already calculated. Shahid has also answered correctly. Yes, Chavez. Second one answer which we have given, that is correct. See, this is very easy. What is the change in potential? Change in potential means potential difference. That is given to you as 20 volt. What is the change in the distance or separation in the radius or the separation between the two points? It is 10 meter. So electric field is what? This is dV, or you can say delta V over delta R. Change in potential, we put a negative sign also. So minus 20 by 10, that is minus 2 Newton per coulomb. All right, so this is just the answer. Quickly note it down, that partial derivation I want you to do. See, when we have to partially derivate a function. So here what happens, you will be using all the three coordinates. First, let us say I am differentiating it along x-axis, right? So this is my question. This is an example which I have taken. V is equal to x square y z square in terms of variable only. If you will understand this, any question you will be able to solve. Now, this is not very important from your board examination. Less questions are only asked from this part. Entrance point of view, this is very important. Those students who have to appear for their NEET, JEE and all entrances after class 12, for them this is very important. For your class 12, it can come, so just be prepared with it. Just understand how to solve it, just in case if it comes, fine. Otherwise, not much questions have come actually in your board examination, but in your school exams it can come, just as a preparation. So V is equal to x square. This is just a random example. Now, firstly, we go by x-axis, EX. So here, remember I've told you this symbol, partial derivation delta. Someone was asking also in the last class, what is this S shape? So this is delta. This symbolizes you are partially differentiating the function. So when I am talking about x-axis, other two quantities apart from x will become constant. It means right now y and z, these two will act as constants, right? Suppose I have 3x square. How do I differentiate 3x square? I keep 3 aside. No, I multiply 3 as it is. I do not make any changes in 3, right? So here also right now for you, otherwise x, y, z, all the three are variables, right? X, Y, Z, all the three are variables for you. But currently this is saying when you are solving it for x-axis, your other two variables, that means y and z, these become the constant. So treat them as a constant while differentiating. Now you'll perform normal, simple differentiation you perform. Just treat y and z as if they are constant. They are not these variables. They are proper constants like 3, 4, 5, such constants they are present. And treat x as a variable. So see, if your y and z, these are constants, so we do not make any changes in constant terms, right? We just bring out the constant term and multiply it with the term. If I have the way in the previous question, we were solving 3x cube, right? Huh. So no, 3x cube we were having. So 3x cube, in 3x cube, 3 got multiplied with the rest of the term. That is how we know how we solve constant multiplied with a function. So if y is a constant here in this term, for me in this term, y is a constant. So y will come here as it is. Let me write down the constant. Y will come as it is, no changes. And z is also a constant. So z square is a constant. So z square will be as it is. No changes in here. I'll put the negative sign. Don't worry about the negative sign. Negative sign will come. All right. So y z square, right? Because this is a constant for me. Y z square. This is just a constant term for me right now. Fine. So this becomes when we are solving this, x square is left. Now which variable is left? Now only x square is left. So x square is not a constant term for us. X square is a variable term. So we have to perform differentiation of x square. How to differentiate x square? Tarif, what will be the answer if you differentiate x square? Yes, Madhya. Yes, Tarif?
And next n minus 1.
That is the formula. So put in x square. If it is there, x to the power 2 is there. N is 2 for you. The formula which you're saying, that is general.
2x, 2 minus 1.
See, it will become 2x. You are correct. To the power
2 minus 1.
2 minus 1. That is 1. So 2x to the power 1 is 2x only. So Madiha, Faiza have also correctly answered, and Tarif, you are also right. Good. So x square will become 2x. So what will be your answer? Your answer for the first part will become minus y z square 2x. All right. Now coming to y-axis. When we are coming to y-axis, now you are partially differentiating potential along y-axis with now y will act as a variable to you, and other two quantities, that is z and x, these will act as constant terms. So x and z, the other two which are left, that act as constant. So in this equation, now in this equation, x and z, they both are constant. So you will put x square as it is, z square as it is, right? There won't be any difference in this because these are constant terms. And how do you treat constant terms? You just multiply them as it is. And what is left now? Y. See, if you differentiate y, just y, dy over dy will become 1 only. It means this is simply 1. So what will be the answer? Minus x square z square, right? Because dy over dy is 1, dx over dx is 1, dz over dz is 1. So minus x square z square, this will become as it is. Now coming to third one, that is z axis. When we are talking about z axis, this is partial differentiation of potential with respect to z axis. So now your x and y will act as constant when you're talking about potential gradient across this. So now see, now your x and y, both of these are the constant terms for you. So x and y, this entire term is constant. Minus x minus y x square 2z, perfect match. This is how you will solve. Because see class, x square y will come here as it is, and what is left? Z square is left. So z square, the way Tarif you answered x square, so z square also will be 2z. If x square was 2x, z square also will be 2z. Minus x square y 2z. X square y 2z. Yes, pi's are right. So x square y, this will become 2z. Final answer is minus x square y 2z. So these are the three quantities which you have obtained. But is this your final answer? If I give you potential and I ask you electric field, which answer will you give me out of these? Will you answer Ex, Ey, Ez? Which answer will you give? Right. So this is not the resultant. How to solve it? You have to find out the resultant.
Add.
Yes, add, but vectorically add them. Means suppose it's better if you put Cartesian system, I cap, j cap to differentiate it. What was our first answer that we got along x-axis? Minus y square. How much is minus y? Z square 2x minus y z square 2x. So this becomes I cap plus, then that was minus x square z square j cap plus minus x square y 2z k cap. Now we can solve this at least once we have the values. For example, let me give you the values as well. Just do one thing, note it down till here. Or let me write it down. Suppose here in this question only, in addition to this question, I give you suppose in this part only, I am giving you calculate electric field at 1, 1, 1. So x, y, z is all the value I have given to you, values I have given to you. So what you have to do, just put in the value of 1 in every term. What will be the E net's value? See, 1 multiplied by 1 multiplied by 2 multiplied by 1. So all the terms are 1. That is just minus 2 I cap, right? Here also 1 into 1, that becomes minus j cap. Here also minus 1 square into 1 into 2 into z, that is minus 2 k cap. This at least looks like how to solve this. Minus 2 I cap minus j cap minus 2 k cap. This is not difficult for you. So how to write down the magnitude? This is a part of your basics of vectors. In your class 11th, you do vectors. So that's a basic part. If you have terms in Cartesian form.
Root of Earth.
Yes, good. Who was this? Chavez, I think.
Yes, sir.
Good. Under root you write and then square the coefficients of each term. So this becomes minus 2 square plus minus 1 whole square, because coefficient of j cap is minus 1 here. And plus, what is the coefficient of k cap? Minus 2. Now, whatever is your answer, this will be 4, 1. I think 3 will be the answer. Just check whatever it is. This is the method how to solve it. So partial derivation, if it is asked, this much is sufficient for you whenever you are revising for your exam, any exam, here also, for your school exams, also for your board exam. Just this part is sufficient, because this is the maximum detailed part that we have done. Not even this much part is asked. Usually, if it is, it will be asked. No, a very simpler term will be given than this. It won't even go till here. So this is the maximum thing that will come. Just practice the above part by yourself. See whether the answer is getting matched or not. 3, no, Faiza? You're right. Because this will become root 9, I think, and that will become 3 Newton per Coulomb. Just so do not worry about this part. Just you have to understand how to solve the basic part of it. Again, I would suggest you write down the question v is equal to x square y z square. Keep writing by yourself without copying it from the screen. Wherever you get stuck, look at the answer and everything is present on the screen. And just check what answer you have written and what answer I have written. Are they matching? Wherever you're not able to understand, you can ask me. But this part is sufficient. Just go through this part, and the 1,1,1 question that we have done, that is sufficient for partial derivation. Note it down. Now we'll move on to the next topic. This electric potential gradient also we have done in detail. And this is it. Electric potential gradient is this. We'll do equipotential surfaces next. Now class, the next topic, this is equipotential surfaces. So I hope we'll be able to complete equipotential surfaces in today's class only. This is not a very lengthy topic. It's a very, very easy topic, just a theoretical topic. The way you had no electric field lines from your first lesson, where it was just properties of electric field lines and just a theory part of it. Similarly, equipotential surfaces are there. But equipotential surfaces have a lot of significance. The way electric field lines have a lot of significance, you have been using it in the questions it mentions. Similarly, here also under equipotential surfaces, you will be having the concept indirectly. Questions can come directly, also mention the properties of equipotential surfaces, what will be the work done in equipotential surfaces. This can be given to you. Apart from this, some in your numericals, it will be given to you. An equipotential surface is having this like this. So there also you have to relate. So equipotential, from the term also you can understand equipotential. Equi means equal, and potential, you have already studied what is meant by potential. So a surface where potential remains equal, that will be equipotential surface. So a surface where potential is not changing. For an example, look at this sphere which I have drawn with the charge q. Suppose I choose a point. Here I have chosen a point, point A. Here I am seeing the potential is 2 volt. Coming to this point B, here also I'm seeing the potential is coming 2 volt. Then this is point C, here potential is coming 2 volt. So what can you conclude if I tell you that all the potentials values for A, B, C, these are 12 volt, 2 volt. It means potential at A is equal to potential at B is equal to potential at E, which is just equal to 2 volts. So this, then you can conclude this is an equipotential surface. Any surface where potential's value is not changing with respect to distance. Right now, with the topic which you were studying, this is just contrary to what you have studied. There, everything was changing with respect to potential, right? Everything was changing with respect to distance. Potential itself got changed with respect to position, right? Potential was changing. That's why we had potential gradient. This is just opposite. Potential isn't changing. If I want to say that this surface, this is a random surface that I have drawn. If I want to say that this surface is an equipotential surfaces, all the values of potential A, B, C, all should be the same. All should have the same value of potential. That if you pick a potential at any particular surface, you get the same value throughout that area. All right, so surface at which every point has same potential, VA is equal to VB is equal to VC is equal to 2 volt, and where all the potentials are same. So just some properties are there. Note down this page, we'll see the properties of it. This is an easy topic, you will be able to manage. All right, note down. See, coming to the properties of equipotential surface. So first point says that potential at every point on the equipotential surface is same. So if you choose any particular point, A point, B point, C point, values of potential VA is equal to VB is equal to VC should be same. So potential at every point on the equipotential surface is same. Second point says that, see, if potential is same, means potential is not changing. There isn't change in the potential. So what will be final potential minus initial potential?
0.
0, right? So work done will also be charge multiplied by 0. That is 0. This is a very important conclusion because your most of the questions will have an equipotential surface is 0 and so the details will be given. So work done will also be given to you indirectly if it is saying that equipotential surface is given. If it is saying equipotential surface is there, directly your work done will be 0. Because see, final potential is minus initial potential will be 0 because your final potential is equal to initial potential. They cancel off each other and the change in potential comes out to be 0. Right? So this is the most important point of all the properties which are present. Work done, this is charge multiplied by the change in potential. So work done is equal to charge into 0. All right. Then see, electric field is always perpendicular to the surface. As in, this is your dr, for example, where your electric field is changing. Electric field will always be perpendicular to the equipotential surface. So if you have to, sometimes it comes to draw electric field. So just drop the perpendiculars. All right. And whenever you are mentioning the properties, always try to make this figure and then explain that electric field is perpendicular to the equipotential surface. Last property, this says that wherever you see equipotential surfaces are placed closer to each other, that indicates stronger electric field is present. And wherever you see they are separated from each other, they are far apart from each other, that indicates weak electric field is present comparatively, right? So if they both first in this space, this and this 1 and 2 are very close to each other, right? 1 and 2 are very close to each other. So electric field in this region is stronger, whereas from 2 and 3, if you look, this is the space is wider. So electric field in this region is less. Why? What is the logic? Reason is that when you put in the formula E is equal to minus dV over dr, your electric field is inversely proportional to radius. Here radius is less, distance is less, electric field will be more. Here radius is more, distance is more, electric field will be less. This is what is the logic behind. So just these 4 properties are enough. I am once again repeating the properties. Wherever doubts you have, let me know. First property says that potential at every point is 0 at the equipotential surface. Second point says that work done will be 0 because change in potential is 0. And third point says that electric field is perpendicular to equipotential surface. Last point says that wherever electric field lines are closed, equipotential surfaces are closed, stronger electric field lines are present. And where they are weak, equipotential surfaces are at distance from each other.
Ma'am,
Yes, say.
where there is more electric field, there is more equipotential surface.
Electric field is more, where electric field is more. See,
Yes.
you are talking about in terms of distance.
When electric field is more, so equipotential surface is more.
See, that doesn't make your equipotential surfaces present. Equipotential surfaces are surface. They are not your electric field lines. That electric field lines will be more. Electric field lines are more when stronger electric field is there. Equipotential surface is just a surface. It can be a sphere of radius r. It can be a cube. So if 2 are placed close to each other, then you can tell about the nature of electric field. Otherwise, which you are mentioning, this is the property of electric field line. They will be placed close to each other. All right.
Okay.
Okay, note down from here. Class, this type of question is also asked sometime to draw isolated point charge. So if this is asked, no, suppose charge Q is given, draw isolated point charge. So equipotential surfaces around this charge, they'll be just concentric circles like this. There should be equal gapping between them, but obviously this is difficult to draw. Otherwise, this is equal gapping between them. Like this. This is how we draw equipotential surfaces. Nextly, if you have two positive charges, see, plus Q and plus Q are given. So two positive charges mean same sign. See, in this case, how you draw. You will be drawing concentric spheres only. It's just that, suppose this is it, this is the first one, this is the second one. This will be closer at the far away end and there will be a gap here. This will be closer here and a gap here, like this. This is closer here, larger gap will be here. Closer gap will be here and larger gap will be here. Like this. This is how you'll draw. But if dipole moment is given, why do we draw like this? Because see, electric fields are in opposite direction here because of both the same charges. That's why there is a lot of separation between the equipotential surfaces. If suppose dipole is given to you, plus Q and minus Q, that is what is meant by dipole. Then look, opposite will occur. Now electric fields will be in the same direction here at this point. So they'll be concentrated closer here and separated here. So they will be concentrated here and separated here. They will be concentrated here, separated here. All right, concentrated here and separated here. This is how you drop the dipole. Now see, if electric field is given uniform electric field lines are mentioned. So I think someone was asking also regarding electric field lines and all. If uniform electric fields are provided, then there is equal spacing between all the equipotential surfaces. So they are equidistant. Means equal spacing. Right. But if it is non-uniform, so again, wherever electric field is stronger, more number of equipotential surfaces are there. There will be a gap where electric field lines are lesser. So you were asking, or someone was asking also. So in non-uniform electric field, you get such a case. All right, so there is less separation. Here there is a lot of separation and they'll be at present at random distance. Here the distance, this is going to be random distance. So at random distances, equipotential surfaces will be placed. Fine. So these can come apart from the properties just to draw. So you just have to draw as it is. Even if this is a negative charge, same thing can occur for negative charge. Same thing. Because they'll also be electric fields in opposite direction. Fine. Write down it. This is for isolated point charge. Done, class? Just text me done in the chat column. Class, just wait for 5 minutes for your after class assessment. All right. So now I just need one more class to complete this electric potential energy part. Then potential part will be over and we'll be just left with capacitance, and this lesson will also be over. So capacitance is also not a lengthy part. One more class I need for electric potential energy. Please wait, class. All right, just wait. Thank you so much, class.
Thank you, ma'am.